You have some required reading related to the topic of today's class, which is density-dependent population growth. The first reading comes from Population Ecology First Principles, Second Edition. I personally have had some trouble accessing that resource through my links from off campus. After the first few days of class, I changed the link and it's working better for me now. But in order for me to be able to access that resource from off campus, I also had to log into the OneSearch system, and there's some instructions on how to do that on the D2L. If you still aren't able to access the book, then I think the next thing to do is to search for its title in the library catalog. And if that doesn't work, then I would contact a librarian to ask for assistance to be able to uh, find that book while you're off campus. The other two resources, I haven't had too much difficulty with being able to access them from off campus. So why do populations stop growing? Here's a graph of human population growth, and you see that it's growing exponentially. And the thing about exponential growth is that the per capita birth rate and the per capita death rate are constant. So even when the population size gets really large, mortality stays the same and reproduction stays the same. And it's actually even worse than that because the population size is now really large. So not only do you have a birth rate that hasn't changed, even though there's more crowding going on, but there are more individuals that are doing the reproducing. So you get many, many individuals into the next generation, and the population grows faster than it would if it were growing linearly. One reason why this isn't very realistic is because eventually resources will become too strained and won't be able to support this unbounded growth, and either the birth rate is going to go down or the mortality rate is going to go up. Here's a picture. So the idea is that as the density of sheep gets very large, they run out of space on the ledge, and the mortality rate of sheep increases through some of them falling off the ledge. Today's lecture focuses around the idea of density dependence. So what is density dependent? Well, density dependent population growth occurs when the per capita population growth rate changes as the population density increases. Because it changes with population density, density dependent growth is not exponential. Right now we're going to focus on negative density dependence, and that means that as population density increases, we see a decrease in the intrinsic growth rate. So if you were to graph that, the intrinsic growth rate versus population density, your graph of that would have a negative slope. And that's when we call it negative density dependence. Later in the class, we will talk about positive density dependence when we talk about what an Allee effect is. We've been talking about the per capita growth rate and defining our definition of density dependence. The per capita growth rate is the change in the growth rate per individual, and there are two different formulas for calculating it depending on whether you're working in continuous time or discrete time. In continuous time, it's simply the rate of change in the population divided by the number of individuals in the population. We'll have some practice working with that formula in a couple of slides. So here on the left, we have exponential population growth, and on the right, we have a more realistic scenario, logistic growth, which matches very well with the dynamics of this paramecium population taken from a laboratory setting. At this point, I would like to derive the logistic growth equation by thinking about how population density puts strain on a limiting resource. Throughout this derivation, I talk mostly about food as being the limiting resource, but it doesn't have to be food, it could be something else. So at this point, I would pause this video and watch the video that shows the derivation. The derivation that I go through is based on the book Population Ecology, and so you can also read that book for a slightly different way of describing the same thing. This derivation describes the rationale behind the logistic growth equation, that it comes from an idea that you have limiting resources. So now we can compare what the logistic growth equation looks like as compared to the exponential growth equation. And you'll see that at early time, when the population density is low, the exponential growth and the logistic growth are pretty much the same. It's only once the population density gets very large that you see a difference between the logistic and the exponential growth equations. And if you look at the logistic growth equation that I have graphed on the left, you'll see that it actually looks fairly similar to what we're seeing for the population dynamics of the paramecium population. Now we want to do some calculations. I want to calculate the per capita growth rate for the exponential growth and for the logistic growth equations in continuous time. And after you've calculated that growth rate, I want you to try and draw a graph of it as a function of population size. So you're going to sketch a graph, and on the y-axis you have per capita growth rate, and on the x-axis you have population size. And you're going to do that for both the exponential and the logistic equation. So here are some formulas that'll help with that. You've got the per capita growth rate for continuous time. It's just the rate of change in the population size divided by the population size. You've got your equation for exponential growth and your equation for logistic growth. So from those formulas, you should be able to figure out the per capita growth rate for both the exponential growth and the logistic growth equation. And then when you've done that, you want to represent your answer on a graph like this. So you have population size and the per capita growth rate. So at this point, take out a piece of paper, start working on that problem. Okay, so working with these equations, for the per capita growth rate for exponential growth, you should have got R. And for logistic growth, you should have got R multiplied by, all in brackets, 1 minus n over k. So in the first case, for exponential growth, the intrinsic rate of growth is constant and it doesn't depend on n at all. So that would look like a straight line with height r, and it doesn't change with population density. It's just equal to r, straight line. If we go back for logistic growth, you have r multiplied by 1 minus n over k. So this is a linear equation, and the slope of that linear equation, so it's linear because it has an n in it, and the coefficient in front of the n is minus r over k if you take that r and multiply it through into the brackets. So the slope of your logistic per capita growth rate here is minus r over k, where k is the carrying capacity. So that slope is minus r over k, and the intercept is positive r, because if you go back to this equation and if you multiply the r through, you've got r minus r over k multiplied by n. So that's an equation for a linear relationship where the intercept is r and the slope is minus r over k. So this is a picture that you come up with. The per capita growth rate for logistic growth is equal to 0 when n of t is equal to k. So this intercept here is equal to the value of k, which is the carrying capacity and the maximum number of individuals that the population can have. So logistic growth assumes that the per capita growth rate decreases linearly as a function of population size. At low densities, the population grows at the same rate that it would if it were growing exponentially. The population growth rate, dn dt, is 0, meaning that the population size is not changing, when the population size is equal to K, which is the carrying capacity. Another type of density dependence is a relationship between density and yield for a crop species that's planted. Again, this material comes from your textbook, Population Ecology by Vandermeer. So here we have an expression for the density of crops that are planted and the yield that a farmer actually gets from those crops. So the variables in this equation are N of t, which is the planting density, and Y of t, which is the yield at harvest time for crops that were planted at time t. A is a constant that affects the saturation rate, and W max is the per unit density yield at low planting density. So to understand what the parameter A is, you can look at the graph down the bottom. So on this graph, on the x-axis, we have the planting density in bushels per grain per acre. And on the y-axis, we have the harvest yield, which is the number of plants per acre. And you see that the relationship saturates. So at some point, the farmer can choose to plant his crops more and more dense, but he's not actually going to see big gains in terms of the yield that he gets from doing so. So the relationship saturates, and you don't get much more gain from planting at higher density. And the rate that that saturation occurs at is determined by the parameter A. So this is how quickly the relationship saturates. And the parameter W max determines the slope of this relationship when the planting density is very small. So this is when the number of bushels of grain per acre is very close to zero. So what's the slope around that point of the graph? That's what W max gives you. And so this is an example of density-dependent growth as well, because if you calculate the yield per unit density planted, then you would have an equation which is W max divided by 1 plus A times N. And that relationship depends on density because N is showing up in that per density yield equation. So because the relationship between yield and density is not just a linear relationship, this is another example of density-dependent growth. So now let's look at some actual examples of populations that grow logistically. One example is the human population in the United States of America in the 19th century. So you're seeing two different things plotted here. In red, you see the per capita growth rate over time. And in blue, you're seeing the population size as it changes over time. And so you see that the per capita growth rate is decreasing. And at the same time, as time goes on, the population density is increasing. And this relationship is consistent with logistic growth. And so I just want to point out the graph that we saw earlier, which was the per capita growth rate. We weren't plotting that against time, we were plotting that against population density. So this is a slightly different way of plotting that, but you could figure out what population density is by reading it off of this graph here. But you can kind of see that this is showing increasing population growth, but it's not increasing nearly as fast as it would be if it was exponential growth, and it looks like this population is tending towards a carrying capacity. We already saw this example of paramecium in a laboratory. So we can plot just the population density versus time. This is a graph that we've been looking at a few times so far. Or we can plot the intrinsic rate of increase as a function of population density. And for this to be logistic growth, then we would need to see a linear relationship and we need to see a negative slope. And again, if it's logistic growth, that the slope is going to be minus r over k. And so plotting the data this way, you do see a roughly linear relationship between the intrinsic rate of growth and the population density. Here's an example from a sheep population. So this is a population of sheep that lived on an island in Tasmania, part of Australia, between 1800 and 1925. You can see that the population growth rate is leveling off, or the population size is leveling off, and the population growth rate is going to zero when that happens. Here are some other examples: the buffalo population in the Serengeti, laboratory population of yeast, and barnacles in the marine environment, all growing logistically, all showing growth rates that go to zero when population density gets high, and you're seeing them reach some kind of carrying capacity and level off. Another example is the amphipod Daphnia pulex. So this is an aquatic invertebrate, a zooplankton. And here they're not plotting the population size versus time, but instead plotting the per capita growth rate as a function of density. And here you see a really nice linear relationship suggesting that this population is growing logistically. For the density yield relationship, we have some data on maize, which is just another name for corn, rapeseed, and beets. And if you look at that data in the top left corner, you can see a relationship that looks like it's saturating for the rapeseed. So here's a picture of rapeseed over here, also called canola in Canada, but not in this textbook, I guess. You see a saturating relationship, and it looks somewhat similar to the Shinozaki-Kira equation that we discussed earlier. So, agricultural populations growing according to a density-dependent relationship. We talked about this with exponential growth, that you start off by thinking about the factors that are increasing or decreasing the population, but that equation only tells you if the population is increasing or decreasing. It doesn't tell you what the population size actually is, and oftentimes you want to know that quantity. So you can also solve a logistic growth equation and come up with a general expression, so that if you just know all the parameters in the equation, which would be the initial population size, N0, the reproductive rate at low density, R, and the carrying capacity, K, then you can figure out what the population size is going to be at any point in time. And here's a little animation that illustrates what happens for logistic growth. It's kind of nice because it has a spatial representation of what's happening. So starting off again, you see that the population is spreading and growing and eventually leveling off. So here the resource that's limiting is space. So just going back to the presentation. Here's a little question just to check that you're that you guys are fully understanding what I'm saying here. So we have the equation for logistic growth that describes whether the population is increasing or not, and then we have the general equation that describes the size of the population at time t. So I have a couple of questions for you. Firstly, for the graph that's on the right of the Paramecium population, what's a good estimate for K from the carrying capacity? So can you read the value of the carrying capacity off that graph? And the second question is, if we assume that R is equal to 0.45 and that the initial population size is equal to 1, then can you calculate the size of the population at time t equals 10, 20, and 30? So you guys already have a piece of paper that you've done a problem on already. Let's add this problem to that list. And if you didn't bring your calculator and you need to know what some values of numbers exponentiated are, there's some numbers down the bottom that might be helpful for you. So if you've completed that problem, then I just wanted to quickly summarize some of the things that are important to know about logistic growth. The main points are exponential growth is unbounded because the per capita reproductive rate is constant. For models with negative density dependence, the per capita reproductive rate decreases with increasing population size. And an example of density dependent growth is the logistic equation.